Hi, I'm Nick and I'm with Jacob, and Kevin. We are Group B8 and today we're talking about nested quantifiers. First of all, we'll quickly go over what a quantifier is. A quantifier is either for all, which is this symbol here, or exists, which is this symbol here. For all simply states that for all of that variable, let's say x, the expression is true, whilst exists simply states that for a single, at least one of those variables x, the expression is true. Now we're going to look at nested quantifiers, which when you have two different variables and you need to have therefore two different quantifiers. First we're going to be looking at this quantifier here, two universal quantifiers put together, sorry. As we can see, looking at the table, we can see that there are four possible combinations for the quantification of two variables. That's not to say you can only have two variables, however, we're just going to deal with that first. The first example, this one here, which I just highlighted previously, deals with two universal quantifiers. As both are universal, the order does not matter. This is the same if I was to have two existential quantifiers. However, this is not true for rows 2 and 3. We'll get to those later. Now, going back to the first example, we can see that the predicate p of xy takes in two variables and returns a truth value. For this to be true, p of xy is true for every pair of xy. For example, let's let p xy be the statement that x plus y equals y plus x. And we're going to make this true for every single by putting in these quantifiers, which is not working, for every pair of x and y. Now, using basic math, we know this is true. 1 plus 2 is equal to 2 plus 1. And we know that's true for every single number, or in the mathematical dictionary, because that is the commutative law of mathematics. Now we're going to look at the last example, row 4, which is existential quantifiers. In this case, we see that there is only one pair of x and y where p x and y returns true. An example of this case would be, for it to say, we'll let p x and y be the predicate that x plus y equals 3. Now we know that there's only two pairs of x and y with this value would return true for, when x equals 1 and y equals 2, or when x equals 2 and y equals 1. Note that the domain of x and y in this case are the set of real positive integer values. Now moving on to the more complicated cases. We can consider the second and the third row of table 1. Although they look similar, the variables are bound differently. In the second row, the statement is saying that for every x, there exists a y if the predicate p x or y is true. On the other hand, in the third row, the statement is saying that there exists an x for every y is true for all y. This may be difficult to understand, so we will illustrate this with an example. So let's say we let p x or y, where the domains of x and y are all people. And we're going to let p x or y mean that x loves y. The statement is saying that for every, and then now we're going to add some universal and existential quantifiers, specifically these ones. Now what this statement says is that there's that for every person x, there exists a person y who loves him or her. So that for every x, there is a y that loves them. However, for the statement there exists a y, ax, pxy, that's what they're saying is that there's a person y. Oh, that should be an x, I'm so sorry. What this statement is saying that for a person x loves every person y. For each person. As you can see, these two statements are not logically valid. Consider the world where every person loves themselves but no one else. Then the statement in row 2 would be true, but the statement in row 3 would be not true. Hence the idea that they're not logically valid. Although this table only covers cases with two nested quantifiers, this is not necessarily always the case. For example, consider the predicate p, x, y, z, which means that x plus y equals z. Let me write that out. X plus y equals z. And we're going to let the domains of x, y, and z be all real numbers. The statement there exists a z for all x and for all y means that for every pair x and y there exists a z such that p x plus y equals z. Therefore, the quantifiers in this case are there exists a z for all x and for all y. P, x, y, and z. Saying that for every pair of x plus y, there exists a z. And now we know this to be true. After this we can move on to negated quantifiers and the negation of nested quantifiers. So here we can see the basic rules when it comes to negating quantifiers. If you start off with an existential quantifier, you can negate it to a universal, and vice versa. Using our previous example with three nested quantifiers, we can negate the statement to say that 1. It is not the case for all x, y, and z that there is such that x plus y equals z. So let's just write out the previous statement again. Negating the statement, we see that if we put the not symbol in front and pushing the not symbol through, we can see that. And continuing along. Until we finally get not p, x, y, and z. Oh, that's a mistake, sorry. That should be E, x, E, y. And hence we can see how we started from step 1 to step 4 of negating nested quantifiers.